Alright, we're going to extend our concepts of numbers. And this is something that we're going to repeat over the next couple of modules as we look at tools we can use for numbers. And one of the first things that happened was that the natural numbers, which we've talked about before, or the counting numbers, ran into some problems. And the problems that we run into differed from culture to culture. Right? In India, they invent a zero, and we'll have this idea of whole numbers, which are natural numbers with a zero. Why did I go? Should go 4 to 5. And in Greek culture, they invent integers. Well, in actually Babylonian culture. And so the integers get a double typed Z from German. And what happens with integers is there's an idea of position. Zero's there, and less than 0 is there. And what had happened, at least the first historical way we think of integers existing, was in Babylonian times. They're one of the first agrarian cultures, and they're storing wheat. And so you had the first time that people moved from hunter-gatherers into an agricultural system, and they're all putting bushels of wheat in. But not everyone's farming anymore. You get the first little city towns that manage farms, and you get people that specialize. And so to specialize, they have to develop different types of commerce, which means that everyone can't grow food for themselves. So the people that do own land growing food get taxed, and extra grain gets filled into grain silos. And so you get 3 bushels per acre, right, that you have to tax in. Well, if there was a bad year and you couldn't pay the tax, the idea of a negative number of bushels, or that you owed something, came into play. As the Babylonians had this first idea of positive or negative numbers based off the idea of owing money, or owing something being relative to having nothing. And so what we're going to look at for integers is that we look at a way of dealing with things that are more than 0 or less than 0 by having sign. And sign is similar. We can think of it analogous to direction. And it's our direction away from 0. So positive numbers move to the right visually, and negative numbers move to the left. And so if we start at 0 on a number line, and we move in a positive direction, and get larger to the right and smaller to the left. Integers still only appear in intervals of 1, but we now have this idea of position. And so we can write the positive sign, and we can write the negative sign. We tend not to write the positive or the negative. And notice 0 is a boundary. It is neither negative or positive. And this positional concept brings about some ideas that we can have with numbers. So what we'll do is we'll make a number line for integers. We'll make a line that holds position, and on that line we have 0 as our reference point. And then what we can do is we can graph different numbers. So -3, let me do my graph here. So -1, -2, -3. Well, to graph positionally on a number line, we fill in a circle for the point where a number actually exists. And let's graph 4 on the number line. And so we'll fill in position 4, and we'll graph 0. And now what we can do is we can talk about value. We can talk about bigger numbers being more, just like we do in counting, than smaller numbers. And we can talk about numbers getting much less. When you owe a lot more money, that's or not just money, sorry, personal life intruding in there. When you owe more things than you have, that is less. It has the concept of lesser. And so what we can do is we can use the concept of the number line to compare numbers. So -4 is less than -1 because on a number line, -4 is to the left. And so less than points to the smaller thing. Now we could also say -1 is bigger than or greater than -4, because again, it points to the smaller number. And so we can talk about less than or greater than. And we call these symbols inequality symbols because they talk about something not being equal. And they're useful ways for comparing the value of numbers. Right? And so some examples. -4 as compared to 3, I'll point to the smaller number. I'll point towards the number that's furthest to the left on the number line. So -1 to -5. If -1 is here and -5 is here, as I go to the left I get smaller. So -5 is smaller than -1. If I compare -5 to -2, well, -2 is here and -5 is here, so -5 is smaller. And 0 and -3. Well, 0 is here, -3 is smaller than 0. And so we have the ability to compare the value of numbers. Now, these inequality symbols have companions. We can also have less than or equal to and greater than or equal to. And that means that we can have values that are equal to or less than. And so if I have some number less than or equal to another, 2 is less than or equal to 9, and 9 is less than or equal to 9 because of the equal to. And we'll find that once we start using variables more, this is a great way of talking about a range of numbers if I include the boundary of 9, or if I don't include the boundary of 9. And we'll find as we go into real numbers, these become important ways of not just comparing, but talking about a range of numbers. And so inequalities are useful ways for showing value and beginning to grab a collection of numbers. Now, we have another concept called the absolute value of a number. And I'm going to look at 0 and 1, 2, 3, 4, negative, whoops, that's not negative, that's positive, +4, and -4. And if we were to measure the distance from 0 to either number, well, distance doesn't care about the direction. And so the distance from 0 to 4 is 4, and the distance from 0 to -4 is also 4. And so what we do is we'll write the absolute value. We'll put 2 bars. And whatever the absolute value is it's talking about the distance the number is from 0. And so absolute values are never negative. They're always positive. Now, there's another way of writing absolute value that hints at some deeper mathematical secrets, but I can take the number and square it and take its square root. And one of the things we'll find when we square a number, a negative times a negative is a positive, and so when I take the square root of 9, I get the positive value back. And so there's two ways to think about this. The way I always taught was that for some number, the absolute value is that number without any sign. And there is, if a is greater than 0, then we write whatever it is. If a is less than 0, we take the opposite because that removes the sign. Well, that looks sloppy. Or it's the square root of the number squared. And I like to say the absolute value is we drop the sign. But you'll see these other definitions we'll talk about in the future as we develop deeper concepts, especially this, because this works well with distance, even in 2 and 3 dimensions. And so there's something about this mathematical way of representing something that's very akin to the concept of distance. And this is what we're building, is the idea of distance. And our reference point for distance is the number 0. So let's look at finding some absolute values. And we'll use, so if I want the absolute value of -3, well, I want to look at it, drop the sign. So it's 3. I'm also going to look at it from this definition. These say the same things, so they're mathematically similar. And so there are things that we can learn from these ideas. But in general, absolute value, drop the sign. I guess I could think of it as +5, 5, but the answer of an absolute value will always be positive. It will always be greater than 0, as it's the distance from 0. Now, because integers have direction to them, addition kind of talks about direction. And so we can make some rules for adding integers. So let's do some rules for adding integers. So if they have the same signs, if they have the same signs, add the absolute values. Just going to abbreviate that. And then in what their sign was, is the sign of the answer. If they have different signs, I'll just put different signs. Then in subtract the smaller absolute value from the larger absolute value. The sign of the answer is the sign of the larger absolute value. So let's look at a couple of these. So negative 11 plus negative 15. Well, the absolute value is 11 plus 15, or 26. But the sign was negative on each. And so what we can say is negative 11 plus negative 15 is negative 26. This is the same as starting at negative 11 on the number line and moving 15 in the negative direction. Taking us to negative 26. So let's look at another. Negative 13 plus 4. So we'll take the absolute values and we'll subtract 13 minus 4, which is 9. But the larger absolute value was negative 13. So negative 13 plus 4 is negative 9. Well, it's the same as on the number line. Starting at negative 13 and moving in the positive direction 4. And we would end up on 9. Negative 9. Sorry, negative 9. And so addition is like moving in the direction of the number next to it. So I start at negative 13, I move in the positive 4 direction. I start at negative 13, move 4 in the positive direction. And I end up on negative 9. And let's look at another one. 13 plus negative 6. So I start at 13 and I move 6 in the negative direction. Or we could say this is the same as 13 minus 6, which is 7. And the sign of the largest number was positive, so it's 7. And so integers and addition and subtraction of integers has us move directionally across the number line. A way of thinking about this is a thermometer with a 0 on it, and your positive is above the 0 and negative is below 0. And so we could go negative 13 degrees plus 4 degrees while I'm moving up the scale, but I only get up to negative 9 degrees. And so a thermometer analogy, I think, is something that up in New England, we definitely see this side of the scale a bit more, and we get used to moving from negative to positive numbers. Well, this lets us talk about opposites, or what's known as additive inverses. And this is a very important property about numbers that we're going to use to do other things with. And so if I have a number, its additive inverse has its opposite sign. So if I have 18, its additive inverse is negative 18. If I have negative 5, its additive inverse is 5. And a special thing happens with additive inverses. 18 plus negative 18 is 0. Negative 5 plus 5 is 0. In fact, I can say any number plus its additive inverse is 0. And that makes us do something really neat. We can take two different things in mathematics and make them one thing. If I say A minus B, I can convert that to an addition. I can say that I can add to A the additive inverse of B. And this means that addition and subtraction are the same thing if we have signed numbers. And this will become a useful thing for us when doing order of operations or trying to change or manipulate numbers around. And when I do the whole PEMDAS representation, parentheses, exponents, roots, multiplication, division, addition, and subtraction, I will talk about these as being the same thing, because I can convert any subtraction into an addition if I have additive inverses. And as we build other sets of numbers besides integers and natural numbers, we'll find these useful relationships continue to pop up. So I can subtract integers, 17 minus negative 11, by converting it to an addition. And so 17 plus 11 equals 28. Now I can say I'm subtracting in the negative direction. I can also look at, I have two negatives coming together. They form a positive. In fact, in my mind, I always kind of see that this picks up and comes down here and makes a plus sign out of it. And for some reason, I've always seen it as being a moving thing. When I see a negative next to a negative, it becomes a positive sign. And that's a rule that we'll have different ways of dealing with for different types of operations. In fact, we can look at this if we have the idea that I have 3 times negative 4. Well, that's the same as adding negative 4 3 times, which is negative 4, negative 8, negative 12. Now, if I have negative 3 times negative 4, we could say that's the same as subtracting negative 4 3 times. Because I'm doing the inverse operation. Or minus 4, so plus 4, plus 4, plus 4, 12. And something has happened here. I have one negative sign, I get a negative back. I have 2 negative signs, and I get a positive. And what we say is when we multiply integers, and I'll say 2 integers, multiply 2 integers, if the signs are the same, the answer is positive. If the signs are different, the answer is negative. Well, let's continue this into some special cases. 0 times negative 4. Well, 0 times any number is going to be 0, because it tells me I'm multiplying negative 4 0 times. Now, if I have 1, 2, 3, I have an odd number of negative signs, then my answer is going to be negative, because negative 2 times negative 3 will be positive 6, but positive 6 times negative 5 is negative 30. So I can go 2, 6, 30, and I have 3 negative signs, so I'll get a negative. If I have an even number of negative signs, then a negative 4 times negative 2 is an even number of negative signs. Negative 4 times negative 2 is negative 8. Negative 8 times negative 5, and negative times negative is positive. And so that's positive 40. Or I could do 4 times 8 times 5 is 40, and I have 2 negative signs, which would be positive. And what I look at is even numbers will give me pairs of negative signs, and each pair combines to give me a positive sign. While odd numbers of negative signs, pairs will come together, but I'll still have a negative sign there. And so the negative sign comes across. And so when we multiply integers, the negative signs, the number of negative signs determine the sign of the answer. And this carries over to exponents. If I have negative 2 squared, I'm multiplying twice, so I would have 2 negative signs, and so it would be positive. Which is why when I said in absolute values, if I square a number, it's always going to be positive. Cube a number, so negative 3 times negative 3 times negative 3, right? Which is negative 27, because I have an odd number of negative signs. So if the exponent is even, the answer is always positive. If the exponent is odd, the answer has the same sign as the factor. Right? So 2 to the third that has a positive sign, so that'll be a positive 8. And this leads to a thing in notation that we have to be careful about. When I am doing exponents, it's ambiguous if this sign is attached to the number or the answer. And so we will say the exponent is attached to the number and the sign is attached to the answer unless I have parentheses. And so in this case we would take negative 6 times negative 6, which is 36. But in this case we're going to have negative 6 times 6, which is negative 36. And so if we do not enclose it in parentheses, the sign is not part of the exponent. This is a hard rule to kind of catch. And when in doubt, I always try to include my parentheses to help not be ambiguous. But if we're going to take something to a power, we need to enclose the sign in parentheses. Now, because division is the reverse of multiplication, and we call divisions a quotient, you will see that I tend to write divisions as A over B instead of A divided by B. We can also write a division as A to B, and this is common in like mainland Europe, like Denmark. Notice what happens here. If I take this sign and combine it with this sign, I've got that one. They're all kind of related symbols. I like this form because once we start doing fractions, it says fractions are related to the concept of division. So something that's happening to the pattern is the same as division. But because division is reverse of multiplication, it was reversing what I saw in the tables, it has the same sign rules. So if I take negative 12 and divide it by 4, it's the same as 12 divided by 4, which is 3. And I look at the number of signs I have, and I only have one, and it's a negative, so the answer is negative. And that's the same as saying negative 3 times 4 is negative 12. Right? Because division and multiplication are reversible, so our sign rules want to be reversible. And so we have the same rule. If we are dividing with two different signs, the answer will be negative. If we're dividing with the same sign, the answer will be positive. And this gives us another inverse called a reciprocal, which we'll look at in more detail as we progress a little bit. But if I have A divided by B, that's the same as A times the reciprocal of B. And the reciprocal is 1 over that. And we'll find out later that this will help us start defining fractions. But again, I am now able to turn multiplications into division. And now I can start talking about my order of operations. And there's a thing that happens where additions are a way of counting. Right, we memorize our counting table, and so if I have two things and I add three things to it and I group them together, that's 5. And that'll always be 5. 2 plus 3 equals 5. And so it's a way of not having to grab our groupings together and recount everything, as we memorize these little facts about our digits and how our digits come together. And subtraction is reversing that. It's saying, hey, if I have 5, and I know 3 was one of the things I added to get to 5, what's the other thing? 5 minus 3 equals 2. Or I could say I had 5, and I used 2. 5 minus 2 equals 3. So subtraction reverses or undoes addition. And addition can reverse or undo subtraction. Right? 3 plus 2 equals 5. And so these things are reversible or back and forth. If we do one thing in one direction, we can do it in the other. Well, then multiplication was a way of doing multiple additions. And so if I had to add the same thing multiple times, we turned it into a multiplication. And division undoes multiplication. 12 divided by 3 equals 4. If I have 12 and I was multiplying by 3, what did I have? I had 12 and I was multiplying by 4. What was my other number? So it lets us reverse these things. Well, and we can say exponents are multiple multiplications. Right, when we defined exponents, we said 2 to the third power was the same as 2 times 2 times 2. And we'll talk later on about taking roots as a way of dealing with exponents. But this leads us to an order of operations. We can put parentheses, exponents and roots, multiplication and divisions, and additions and subtractions. And we perform things in this order. We find parentheses, we do the things inside the parentheses, and then we do exponents first, then we multiply, or divide, or add and subtract, going from left to right when they're the same precedent. And we can kind of think of this as a ladder, and you want to work your way down the ladder to perform a calculation. But we built the concepts up. This lower rung, these things build what's in here. Additions made multiplications. Multiplications made exponents. And so we will find that there are some rules that we'll come up with later where this building is inherent in it. So let's look at an order of operations problem. And so I want to do from the top down. Well, are there any parentheses? No. Are there any exponents? Yes. So I will do the exponents first. So 6 squared is 36. And I'm not going to do anything else but exponents. There should be a plus 1 here. Sorry about that. And so now I've gotten rid of anything on this rung of the ladder, and I'm squarely down on this rung of the ladder. So now I've got to do multiplications and divisions. And I've got to do them left to right. So 36 minus 24 divided by 4 is 6 times 3 plus 1. And I'm going to come back in now and still doing multiplications because I haven't fallen off that rung yet. So 36 minus 18 plus 1. And now we're all on the same rung. So 36 minus 18 is 18 plus 1. Again, going left to right, or 19. And this is how we perform the order of operations. Down the ladder, left to right. Alright, and we'll continue to explore some number theory and number sets and properties of numbers.